Welcome back. Let us continue our discussion about finite difference schemes for parabolic partial differential equations. So we are working on the development of finite difference formulations for partial differential equations. And at the moment we are designing explicit schemes. So one of the explicit schemes we have seen in the last video, in the last lecture, that was forward in time and central in space. So let me have a quick recap and then I'll be moving towards another formulation of finite differencing. So let me share the screen. So we are discussing about finite difference methods for partial differential equations, and we have considered one-dimensional diffusion problem with some initial condition and boundary condition, and of course this alpha is a positive constant. So the scheme we discussed was finite forward in time, central in space. So this time derivative was approximated by forward differencing, so future time level minus the present level divided by the difference in the times, and then second order method for this partial derivatives with respect to the space coordinate. So when we move in space, so we have to fix the time coordinate. So this was finite forward in time, central in space scheme, and after rearranging, we have this expression ui n plus 1 equals to ui at time level n plus alpha delta t by delta x square ui plus 1 negative 2 ui plus ui minus 1 at the time level n. So last time I told you that this is an explicit scheme. So most of the explicit scheme suffer from the stability criteria. So for that, this term here that I denoted as nu for stability, that must be less or equals to 1 by 2. So a scheme is stable if the error will not increase if you move from one iteration to another iteration. So in other words, we could say the solution remains bounded. So this scheme is conditionally stable because this is the condition for stability. This is also known as CFL condition, named by Courant, Friedrich, Lewis condition. So explicit schemes need to satisfy this CFL condition for the stability. So if scheme is stable, then we say that the error will remain bounded and will decay if you move from one iteration to the other iteration, to next iteration. So this is the one meaning of stability. So this is explicit scheme. Explicit schemes generally can be written as the solution at new time is a function of the solution at the old time. So everything that you need is available. So this is available if you are having first iteration. So this will be the initial solution, and if you have some intermediate iteration, then this will be coming from the previous iteration, and this is the update. So we are done with FTCS, and in some video we will generate its MATLAB code, and I will show you how the choice of delta t and delta x affects the solution. So for the choices which give rise to less than half, you will see stability in the solution. Error will not increase from iteration to iteration. And if this condition is not satisfied as a test case, I will intentionally put such cases, such values of delta t and delta x such that this condition is violated, and you will see the solution, what is the behavior of solution. That will be some divergent solution or some oscillatory solution. Okay. Let us move towards another explicit formulation, that is central in time and central in space, also known as CT, CS, and there is the name of this scheme, that is Richardson's method. Richardson's method. So let us see how we go. Same problem. So we are designing schemes for parabolic partial differential equations. So the same problem, partial u by partial t alpha partial to u by partial x2. So now we are saying that we have to move central in time. So central in time mean, so we will freeze the grid point, some location, and if the time level is n and you are applying central scheme, so you have to move forward and you have to move backward. So there will be a space, this step it will be 2 times delta t, and here is central in space like the previous one. So ui plus 1 minus 2 ui plus ui minus 1, and the time level n divided by delta x whole square. So if you could arrange, you could get ui n plus 1 is equals to ui n minus 1 plus alpha. This will be 2 alpha delta t by delta x square, and the rest of the terms here ui plus 1 minus 2 ui plus ui minus 1 at the time level n. Again, this is a kind of explicit scheme, as this new solution depends upon the values from the previous time levels. But there are 2 time levels involved in the pre-processing. Okay, the stability analysis shows you could perform von Neumann stability analysis, or some other stability method to check that this scheme is unconditionally unstable. So this is a bad news, because unconditionally unstable schemes you cannot use. So this is unconditionally unstable for this heat problem, for this parabolic PDE. So let me put, so that you may remember, if we have a scheme like this, means we will throw this scheme for parabolic PDEs. I repeat, we will throw this scheme for parabolic PDEs. I haven't said that we will throw this scheme for all kinds of problems. So please keep in mind, if a scheme is a failure for one kind of problem, it does not mean that it will be a failure for all kinds of problems. Maybe it would work for hyperbolic problems. So a scheme is related with the underlying partial differential equation. So this stability requirement, this is for this parabolic partial differential equation. So now you can understand there are actually three stability conditions that has arisen. There could be a scheme that is conditionally stable, mean there is some condition that if you satisfy, the scheme will be stable, like FTCS for parabolic partial differential equations. There are schemes that are unconditionally unstable, like Richardson scheme, as I have just shown you. And there will be schemes that will be unconditionally stable. So this is the best possible case. There is no requirement on the stability. There is no issue of delta t and delta x for stability requirement. So we could write like this. Sorry. This is the case where you are not able to apply this scheme. And for this, you need to have some extra care. So let me put like this. So some care needed for the selection of, for the choice of time step size and space step size. Here you are free to choose. But there are certain other requirements beside this stability. We also need to take account for accuracy. For accuracy reasons, somewhere we limit our delta t and delta x. But as far as the stability is concerned, unconditionally stable schemes, you are free to choose delta t and delta x. So you cannot use unconditionally unstable schemes because they are unstable no matter what you want to do with these conditions. So the last scheme from this explicit category is the third scheme that I'll show you is the Dufour-Frankel method. Dufour-Frankel method. So again, we will start by the Richardson formulation, the CTCS. Let me write the partial differential equation. So central in time, central in space. The start is the same as in the Richardson case, but there is some modification made by Dufour and Frankel. So central in time mean this expression, central in space divided by delta square. So this is actually the Richardson scheme, which is a case of failure. We have seen this is Richardson scheme, which is a case of failure. But what Dufour and Frankel did, this scheme, if we replace, let me use some other color, if we replace this value at the location I at time level n with some average coming from the two previous time levels. So what I'm saying is that if we take this UIN and we replace this by the average value like this. So this is a time level n, and this is time level n plus 1 and n minus 1. So what we get is ui n plus 1 minus ui n minus 1 divided by 2. Delta t, no change in the left hand side. So ui n I plus 1. Let me erase this. Okay. Plus, let me use this average here. I am replacing this UIN with this term. So minus 2 minus 2, and I am putting with some different color so that you see the change. UI plus UIN minus 1, here we have n plus 1 divided by 2, and then the same term plus ui minus 1 power n, time level n, divided by delta xk. So we have replaced the term uin as the average of the two time levels, uin plus 1 and uin minus 1. And if you rearrange the solution at grid point I time level n plus 1 is on the left hand side, also now it is present on the right hand side. So if you rearrange this, you will be getting, I am skipping some steps, so you will get 1 plus 2 times alpha delta t by delta x whole square uin plus 1 left hand side. So 1 minus 2 alpha delta t by delta x square ui n minus 1 plus last term 2 alpha delta t by delta x whole square ui plus 1 plus ui minus 1 time level n. So that's it. This is the Dufour-Frankel method. This is again, you see, this is explicit method because the solution at location I and at a new time level depends all the information available at the previous time levels. So this is again explicit formulation. But what is surprise? Surprisingly, this scheme is unconditionally stable. So that's a very good news. So what you see, the Richardson scheme, that was a case of failure. The central in time, central in space, that was a case of failure. But with the little modification given by Dufour-Frankel, you have got a scheme which is unconditionally unstable. That is a gain, very big gain. But what is the cost? What you need to pay? So what is the issue? If you look at the stencil, computational stencil, you would realize that now you need two sets of values to feed into the formulation to get the solution at the new time step. So if you look, you need solution information at time level n plus 1 and as well as time level n. So if I draw the computational stencil, you would see the information. So this is time level n, this is n plus 1, this is n minus 1. So we are interested in the solution at this location I, a generic location, and time level n plus 1. Look at the formula that I derived. So you need to have information from the location I at time level n minus 1. So you need to give this information and then two more values from time level n, but from the grid location I plus 1 and I minus 1. You may check this because if you look, this value is coming from time level n minus 1, and from time level n, the information is coming from the location I minus 1 and I plus 1. So when you feed this information, you will get solution at this node. And similarly, you can rotate this node, you can move forward, and again, you can compute. So this scheme is unconditionally stable, so no requirement for stability, no requirement on a combination of delta t and delta x. But you have to have information available at two previous time levels. So this can be accommodated through if you have two initial sets of data to start this procedure, or if you don't have two initial sets of data, you could apply some one-step method as a starter. What I'm saying is that apply some other scheme like FTCS and compute solution at a new time level. This is the given initial solution. When the solution is available at two time levels, then you can of course apply this Dufour-Frankel scheme, which is unconditionally unstable. So that's it. So we have seen three explicit formulations. As a summary, you see FTCS scheme, Richardson scheme, and Dufour-Frankel scheme for parabolic PDEs, for parabolic PDEs. And we have seen this is conditionally stable, this is unconditionally unstable, and unconditionally stable. So in the next video, we will be working on the MATLAB codes of these schemes, and I will perform some simulations to show you this issue of stability, how it gives rise and how we can settle it down. Okay. And if you want to fully avoid the stability requirement, you have to move towards the implicit schemes. That is our future task. So there will be explicit and implicit formulations of parabolic PDEs as well. Okay, thank you very much.